Welcome to this coding walkthrough. Today, we'll be diving into LeetCode problem number 1894, titled Find the Student That Will Replace the Chalk. In this problem, we'll explore how to efficiently determine which student will run out of chalk during a repeated subtraction process. Let's get started. The problem is about determining which student will be responsible for replacing the chalk when the teacher runs out. You are given an array called chalk, where each element represents the amount of chalk a student uses in one turn. Additionally, you are provided with an integer k, which is the initial amount of chalk the teacher has. The process involves students taking turns using their respective amounts of chalk. When the chalk runs out, the student who cannot take their full required amount is identified, and their index is returned. The inputs include the chalk array, where each value is between 1 and 100,000, and the integer k, which can be as large as 1 billion. The output is a single integer representing the index of the student who will need to replace the chalk. In the first example, the chalk array is 5, 1, 5, and k is 22. Initially, the teacher has 22 units of chalk. Student 0 uses 5 units, leaving 17. Then, student 1 uses 1 unit, reducing the chalk to 16. Student 2 uses 5 units, leaving 11. The process repeats. Student 0 uses another 5 units, leaving 6, and student 1 uses 1 more unit, leaving 5. This cycle continues until student 2 uses their 5 units again, leaving 0 chalk. At this point, student 0 is supposed to use 5 units, but there isn't enough chalk left. Therefore, student 0 will replace the chalk, and the output is 0. In the second example, the chalk array is 3, 4, 1, 2, and k is 25. The teacher starts with 25 units of chalk. Student 0 uses 3 units, leaving 22. Then, student 1 uses 4 units, reducing the chalk to 18. Next, student 2 uses 1 unit, leaving 17, and student 3 uses 2 units, leaving 15. The cycle restarts with student 0 using another 3 units, leaving 12. Student 1 then uses 4 more units, reducing the chalk to 8. Student 2 uses 1 more unit, leaving 7, and student 3 uses 2 more units, leaving 5. The cycle continues, and student 0 uses 3 units again, leaving 2. Finally, when it is student 1's turn, they need 4 units, but there is not enough chalk. Therefore, student 1 will replace the chalk, and the output is 1. To summarize the process in the second example, after multiple rounds of students using their allocated amounts of chalk, the teacher eventually runs out of chalk during student 1's turn. This is because student 1 requires 4 units, but only 2 are available. At that point, student 1 is identified as the one who will replace the chalk. This illustrates the key steps of tracking the remaining chalk and determining which student is unable to complete their turn. The constraints ensure that we are working with manageable inputs, even though k can be very large. By efficiently reducing the problem using mathematical observations, we can handle these large values of k effectively. One key observation is that the sum of all values in the chalk array, referred to as total, determines the amount of chalk consumed in one full round through all the students. If k is greater than this total, we can use modulo arithmetic to find the remaining chalk after all possible complete rounds. Once k is reduced, the problem simplifies to iterating through the chalk array to determine which student depletes the remaining chalk. This approach ensures that we achieve a time complexity of O(n), where n is the length of the chalk array. This efficiency is critical given the constraints, as it allows us to solve the problem even for large values of k in large arrays. To tackle this problem, let's first consider the brute force approach. The idea is straightforward. We simulate the process of distributing chalk among the students in a loop. Starting from the first student, we subtract the chalk required by each student from the total k. If at any point k becomes less than the chalk needed by a particular student, that student will be the one to replace the chalk. If k remains non-negative after going through all the students, we simply restart the iteration from the beginning of the array, continuing this process until k is fully exhausted. However, the downside of this method lies in its inefficiency. The time complexity in the worst case is O(n*(m), where n is the number of students and m is the number of iterations required to deplete k. This can become computationally prohibitive, especially when k is very large. While simple to grasp and implement, this approach is not practical for large inputs, as it repeatedly loops over the array, leading to unnecessary computations. Now, to address these inefficiencies, we turn to an optimized solution. The optimized approach leverages the cyclic nature of the problem to minimize redundant computations. Instead of simulating the chalk distribution through repeated iterations, we calculate the total amount of chalk needed for one complete cycle of all students, represented as total equals sum, chalk. If k is greater than or equal to total, it means the process will repeat cyclically. By using k equals k% total, we reduce k to a smaller, manageable value, representing the remaining chalk after accounting for all complete cycles. From here, the task is simplified to a single traversal of the array, where we identify the first student whose chalk requirement exceeds the remaining k. This approach is significantly more efficient, with a time complexity of O(n), as it involves just one computation of the total and a single traversal of the array. Additionally, it avoids redundant iterations and handles large inputs effectively. Recognizing the periodic nature of the problem and applying modulo arithmetic is the key insight here. This makes the optimized approach not only scalable but also clean and straightforward to implement. For these reasons, it is the chosen strategy, offering an ideal balance of efficiency, simplicity, and scalability compared to the brute force method, which is infeasible for larger inputs. To solve this problem, we need to identify the student who will replace the chalk when a given amount, k, is distributed among students in a circular manner. Each student has a specific chalk requirement, represented by the chalk array. The process continues in a loop, with chalk being distributed repeatedly, until k is insufficient to meet the requirement of a student. At that point, we determine the index of the student who causes this insufficiency. The first step in our algorithm is to calculate the total chalk needed for one complete cycle, which we call total_chalk. This is simply the sum of all the elements in the chalk array. If k is larger than or equal to total_chalk, we reduce k by taking it modulo total_chalk. This effectively removes the unnecessary full cycles, leaving us with a smaller, more manageable value of k. Using this optimization ensures that we avoid redundant iterations and improves the efficiency of our solution significantly. Now that we have reduced k to a manageable value, the next step is to iterate through the chalk array. Starting from the first student, we subtract each student's chalk requirement from k. If at any point k becomes less than the chalk required by the current student, we immediately return that student's index, as they will be the one to replace the chalk. Otherwise, we continue to the next student. This process guarantees that we find the correct student within one pass of the array. The algorithm terminates as soon as k becomes insufficient for a student, ensuring minimal computations. By leveraging the circular nature of the problem and the modulo operation in step 1, we avoid simulating the full rotation of students, which would be computationally expensive. This reduces the time complexity to O(n), where n is the size of the chalk array. Additionally, the early exit ensures that we perform the least amount of work necessary to arrive at the solution. In terms of data structures, the solution is straightforward. The chalk array stores the chalk requirements of each student, and we iterate through it once after reducing k. The scalar value k represents the remaining chalk and is dynamically updated during the iteration. For complexity analysis, the time complexity is O(n), where calculating total_chalk takes O(n), and iterating through the array in the worst case also takes O(n). The space complexity is O(1), as we only use a few scalar variables, such as total_chalk and k, in addition to the input array. This ensures that our algorithm is both time and space efficient, making it suitable for a wide range of input sizes. Let's walk through an example to solidify our understanding. Suppose the input is chalk equals 5, 1, 5, and k equals 22. First, we calculate the total chalk for one cycle. Total_chalk equals 5 plus 1 plus 5 equals 11. Then, we reduce k modulo total_chalk, k equals 22%, 11 equals 0. With the updated value of k, we begin iterating through the chalk array. The first student requires 5 chalk, but since k equals 0, it's insufficient. Therefore, we return index 0, as this student will replace the chalk. This example highlights how modulo reduction simplifies the problem and ensures efficiency. For edge cases, if there is only one student, the answer is always 0, as they will inevitably replace the chalk. When k is very large, the modulo operation ensures that the algorithm remains efficient. And if k is exactly equal to total underscore chalk, the modulo operation reduces k to 0, meaning the first student will replace the chalk. These considerations ensure the algorithm is robust and handles all scenarios effectively. The solution to finding the student who will replace the chalk is implemented in the chalk replacer method of the solution class. The problem involves distributing k units of chalk among students in a circular manner, stopping when the chalk runs out for a specific student. Explanation. 1. Step 1. Total chalk for one cycle. The first step computes the total amount of chalk required for one complete cycle, all students. This is calculated as the sum of the chalk array. If k is greater than or equal to this total, we can skip full cycles since the distribution repeats. 2. Step 2. Reduce k using modulo. To optimize the process, we reduce k modulo the total chalk required for one cycle. This effectively removes unnecessary full cycles, leaving us with only the remaining chalk for the incomplete cycle. 3. Step 3. Find the student. We iterate through the chalk array, subtracting the chalk required by each student from k. If at any point k is smaller than the chalk required by the current student, that student is the one who will replace the chalk. The index of this student is returned. 4. Edge case. The algorithm handles edge cases, such as when k is smaller than the chalk required by the first student, ensuring the correct index is returned. The approach is efficient with time complexity O, n, where n is the number of students, as we only iterate through the chalk array once after the initial sum calculation. The space complexity is O, 1, since no additional data structures are used. This is the Java implementation of LeetCode problem number 1894. Find the student that will replace the chalk. The solution mirrors the Python logic exactly, with key differences such as explicit type declarations, the use of Java's primitive data types, and iteration syntax. It first calculates the total chalk required for one complete cycle, reduces k modulo this total, and then iterates through the students to find which one will run out of chalk. This implementation handles edge cases efficiently and adheres to Java conventions. Here, we are solving the problem of finding the student who will replace the chalk. In the first example, the chalk array is 5, 1, 5, and k is 22, representing the amount of chalk available. We start by calculating the total chalk required for one complete cycle of all students. This is simply the sum of the chalk array, which gives us 5 plus 1 plus 5 is equal to 11. Next, we reduce k modulo the total chalk to account for complete cycles. This means we calculate k% total underscore chalk, which results in 22% 11 is equal to 0. So after completing 2 full cycles, no chalk remains. At this point, we determine which student will run out of chalk by iterating through the chalk array. Starting with student 0, we see that they need 5 pieces of chalk, but since k is 0 and less than 5, student 0 is the one who will replace the chalk. The final output is 0. Now, let's look at the second example, where the chalk array is 3, 4, 1, 2, and k is 25. Again, we begin by calculating the total chalk required for one complete cycle, which is the sum of the array, 3 plus 4 plus 1 plus 2 is equal to 10. Then, we reduce k modulo total underscore chalk to handle full cycles. Here, we calculate 25% 10, which gives us 5. This means that after 2 complete cycles, we have 5 pieces of chalk left. To find the student who will run out of chalk, we iterate through the array. Student 0 needs 3 pieces, and subtracting this from k gives us 5 minus 3 is equal to 2. Moving to student 1, they need 4 pieces, but k is now 2, which is less than 4. Therefore, student 1 is the one who will replace the chalk. The final output is 1. In the third example, the chalk array is 2, 2, 3, and k is 7. As before, we start by calculating the total chalk required for one complete cycle. Adding up the array, we get 2 plus 2 plus 3 is equal to 7. Then, we reduce k modulo total underscore chalk. Since k is already equal to 7, calculating 7% 7 gives us 0. This means all 7 pieces of chalk are used up in one complete cycle, leaving no chalk remaining. To determine the student who will replace the chalk, we iterate through the chalk array. Student 0 requires 2 pieces, but since k is 0 and less than 2, student 0 will run out of chalk first. The final output is 0. This final example reinforces the logic of the solution. After reducing k modulo the total chalk required for one cycle, we systematically iterate through the chalk array and subtract each student's chalk requirement from k. The moment k becomes less than the chalk required by a student, that student is identified as the one who will replace the chalk. This approach ensures an efficient solution, handling even large values of k effectively by avoiding unnecessary iterations over full cycles. In this case, student 0 is again the result, and the output is 0. To analyze the time complexity of this solution, we break it down into 3 main steps. First, we calculate the total sum of the chalk array, which we call total_chalk. This involves iterating through the array once, making this step O, n, where n is the number of students. Next, we reduce k by taking it modulo total_chalk. This is a constant time operation, so its complexity is O(1). Finally, we identify the student who will run out of chalk by iterating through the chalk array and subtracting values from k until it becomes less than the current student's chalk requirement. In the worst case, this loop runs through all n students, making it O(n). Combining these steps, the overall time complexity of the solution is dominated by the 2 linear operations, resulting in an O(n) complexity. Now let's examine the space complexity. The algorithm is very efficient in terms of memory usage because it does not rely on additional data structures. We use a few scalar variables, such as total_chalk and the reduced value of k, both of which require constant space. The input array chalk is read-only and does not contribute to additional memory usage. Since no other data structures are created, the overall space complexity is O(1), meaning the solution uses a constant amount of additional space regardless of the size of the input. When comparing this approach to a brute force solution, we see a significant improvement in efficiency. A naive algorithm would involve repeatedly iterating through the chalk array and decrementing k until it becomes smaller than the chalk required by a student. This could result in a time complexity of O(k) in the worst case, as k could be extremely large. In contrast, the optimized solution uses modular arithmetic to reduce k by total_chalk, ensuring that the number of iterations is limited to at most one complete traversal of the array. This improvement brings the time complexity down from O(k) to O(n), making the algorithm much more scalable for large inputs. Finally, let's analyze the best, average, and worst-case scenarios for this solution. In the best case, the student who runs out of chalk is identified during the very first iteration of the loop. However, the computation of total_chalk still dominates, so the time complexity remains O(n). In the average case, the loop iterates through about half of the chalk array, but again, the overall complexity is still O(n), since the asymptotic behavior is determined by the sum and traversal operations. In the worst case, the loop goes through the entire array, which also results in a time complexity of O(n). This consistent linear performance across all cases highlights the efficiency of the optimized approach, especially when compared to the brute force method, which is highly inefficient for large values of k. When solving this problem, there are several common mistakes to be aware of. First, not accounting for large values of k can lead to inefficiencies. For example, if k is much larger than the sum of the chalk array, repeatedly iterating through the array without optimization can cause a time limit exceeded error. Instead, you can use modular arithmetic to reduce k by taking k modulo the total sum of the chalk array. Another common pitfall is relying on floating point arithmetic for calculations like summation or division. This can introduce precision errors in edge cases, so it's better to stick to integer arithmetic throughout the solution. Additionally, failing to reset the loop index correctly when distributing chalk can lead to errors or infinite loops. Modular arithmetic is again helpful here to handle indices cleanly. Lastly, be cautious with edge cases, such as when k is smaller than the first student's chalk requirement. In such cases, the correct answer is to return the first student's index immediately. Missing these scenarios can result in incorrect outputs. Another mistake to avoid is overcomplicating the problem with unnecessary data structures. For example, creating additional arrays to track chalk usage might increase memory usage without adding value. Instead, focus on minimal state representation to keep the solution efficient. Now, let's discuss some key insights for interviews. First, recognizing repetitive patterns is crucial. Problems involving repeated processes, like this one, can often be optimized with modular arithmetic. Here, the total chalk sum defines the cycle length, so reducing k with k modulo sum, chalk, simplifies the problem significantly. Second, optimizing runtime is essential. A brute force solution has a high time complexity of O, and *k/sum, chalk, which is impractical for large inputs. Instead, aim for an O(n) solution by breaking the problem into smaller, manageable parts. Lastly, interviewers often test your handling of edge cases like small arrays, very large k values, or when k gets exhausted early. Demonstrating careful consideration of these scenarios can make a strong impression. As a follow-up, you might be asked how to handle dynamic updates to the chalk array. For such situations, advanced techniques like segment trees or prefix sums might come in handy. This problem also shares similarities with other resource allocation or modular arithmetic problems on LeetCode. For instance, LeetCode 410, split array largest sum, involves distributing resources while minimizing or maximizing a specific metric. LeetCode 189, rotate array, uses modular arithmetic to identify repetitive patterns, making it conceptually related. Another example is LeetCode 1011, capacity to ship packages within D-days, which also requires optimizing resource allocation under constraints. Finally, LeetCode 378, kth smallest element in assorted matrix, shares the concept of reducing large k values intelligently to simplify the solution. Practicing these problems can enhance your understanding of how modular arithmetic and optimization techniques apply across different scenarios. There are multiple approaches to solving this problem, each with its own trade-offs. The brute force approach is straightforward to implement but inefficient for large k or arrays, as it has a time complexity of O, and *k/sum, chalk. A more efficient method is modular arithmetic optimization. By reducing k with k modulo sum, chalk, you can iterate through the chalk array just once, achieving a time complexity of O(n). This is the most efficient solution but requires a good understanding of modular arithmetic. Another approach is using binary search on prefix sums. Here, you pre-compute the prefix sums of the chalk array and use binary search to locate the student who runs out of chalk. This method has a complexity of O(n) for prefix sum computation and O log n for each search, making it slightly slower overall but useful for handling dynamic updates. Finally, simulating the distribution with a circular array is another option. This method relies on modular arithmetic to handle indices but may require additional care for edge cases. Each approach has its strengths, so consider the problem constraints and requirements when choosing the best method. Great job! We've covered how to solve the problem find the student that will replace the chalk using an efficient approach. Remember the importance of modular arithmetic and cumulative sums in optimization. Thank you for watching, and be sure to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!